The mountain rises with such geometric perfection that it almost seems too symmetrical to belong to the natural world. From a distance, it appears motionless, timeless, and invincible, standing above the Swiss Alps like a monument carved by an artist rather than assembled by geological forces. Millions of visitors photograph it every year. Climbers dream of standing on its summit. Scientists, however, have been looking at the same peak through a very different lens. Their instruments reveal that this famous mountain is not standing in quiet stability. It is slowly deforming, cracking, and shedding pieces of itself. Far from being frozen in time, the Matterhorn is engaged in an endless struggle against gravity, weather, and the internal weaknesses created during its remarkable birth. Towering to an elevation of approximately 14,692 feet, or 4,478 meters, the Matterhorn dominates the border between Switzerland and Italy. Its unmistakable pyramid has become one of the world's most recognized mountain profiles, appearing on countless postcards, travel advertisements, and even the inspiration for famous architectural and commercial designs. Yet its iconic appearance conceals a far more complicated reality. Every ridge, every cliff, and every fractured block tells the story of a mountain that never truly stopped changing. Unlike volcanic mountains that grow through eruptions, the Matterhorn owes its existence to one of the greatest continental collisions in Earth's history. Tens of millions of years ago, an ancient ocean known as the Tethys Ocean separated the African and European continents. That ocean gradually disappeared as the African tectonic plate continued its relentless northward movement. Eventually, the oceanic crust between the continents was almost entirely consumed by subduction, forcing the continental masses themselves into collision. When continental crust collides, neither side sinks easily because continental rocks are relatively light compared to the dense oceanic crust. Instead of descending into the mantle, enormous slabs of crust crumple, fold, fracture, and stack upon one another. The process resembles an immense slow-motion traffic accident occurring over millions of years, except the vehicles are entire continents hundreds of miles across. The Alps emerged from this colossal compression. Rocks that once rested on ancient seafloors were thrust thousands of feet upward. Deep crustal rocks experienced tremendous pressure and temperature, transforming their mineral structures before eventually returning toward the surface through uplift and erosion. Entire slices of crust traveled astonishing distances along enormous thrust faults before becoming welded into the growing mountain belt. Matterhorn occupies an especially unusual place within this geological zone because its summit is actually composed of rocks originating from the African continental plate rather than Europe. During the collision, fragments of African crust were transported over European rocks through massive tectonic displacement. Today, geologists can literally walk across one of the most dramatic continental boundaries preserved anywhere on Earth. This remarkable arrangement means that the mountain is built from rocks possessing different origins, different mechanical strengths, and different histories of deformation. Rather than forming one perfectly uniform block, Matterhorn consists of numerous fractured units assembled through violent tectonic events spanning tens of millions of years. Those inherited weaknesses continue influencing the mountain's stability today. Its famous pyramid shape also creates a deceptive impression. Many imagine the mountain as a solid stone monument extending deep underground like an enormous crystal. Reality is far less orderly. Countless fractures intersect the mountain from every direction. Some formed during continental collision, others developed as the immense weight of overlying rocks disappeared through erosion. Additional cracks continue forming today as freeze-thaw cycles, gravity, earthquakes, and changing temperatures constantly reshape the bedrock. Every winter, water enters tiny fractures before freezing into ice. Because ice expands compared to liquid water, the freezing process exerts tremendous outward pressure against the surrounding rock. Even microscopic openings gradually widen after countless seasonal cycles. Eventually, fragments detach from steep cliffs in events ranging from pebble-sized falls to catastrophic rock collapses involving thousands of cubic yards of material. This natural weathering has operated throughout the mountain's existence, but another process has increasingly captured scientific attention during recent decades. Much of Matterhorn's higher elevations contain alpine permafrost, permanently frozen ground, where ice occupies fractures within the bedrock itself. Unlike surface snow that melts each summer, permafrost can remain frozen continuously for centuries or even thousands of years. That frozen ice performs an important structural role. It acts almost like cement, helping bind fractured blocks together. Although rock carries the overwhelming majority of the mountain's weight, frozen ice filling joints contributes additional resistance against movement. Remove that frozen support, and previously stable blocks may begin shifting. Researchers have spent years monitoring this hidden component of alpine stability because temperatures throughout many high mountain regions have increased significantly. Permafrost is no longer simply remaining frozen. In many locations, it has started warming, thawing, and retreating deeper into the mountain. Scientists from the WSL Institute for Snow and Avalanche Research closely monitored one section of the Matterhorn's Hernley Ridge for several years before a dramatic event confirmed their growing concerns. During the summer of 2023, a freestanding rock pillar collapsed after progressive weakening caused by meltwater infiltrating fractures within the permafrost. Approximately 20 cubic meters, or roughly 700 cubic feet, of rock detached from the ridge. Fortunately, nobody was injured, but the event became an important scientific case study rather than merely another routine rockfall. Detailed analysis revealed that water played a far greater role than previously understood. Rather than simply melting surface ice, infiltrating meltwater transported heat deep into fractures. As warmer water penetrated the frozen rock, it accelerated thawing from within. The thawed zones allowed additional water penetration, creating a reinforcing cycle that progressively weakened the mountain's internal structure. Laboratory testing and computer simulations reproduced the observed movement with remarkable accuracy, demonstrating that warming permafrost, groundwater flow, and reduced friction together can destabilize steep alpine rock masses. The reduction in friction proved especially significant. Frozen fractures possess mechanical properties very different from water-filled fractures. As ice disappears, resistance to sliding decreases dramatically, allowing previously locked rock masses to begin creeping under their own enormous weight. Scientists found that thawing can substantially reduce the frictional resistance holding fractured blocks in place, helping explain why sections of the mountain may remain apparently stable for years before eventually failing. This process unfolds gradually enough that visitors standing in Zermatt seldom notice any visible change. The mountain still appears majestic against the skyline. Its famous ridges still cast the same dramatic shadows across surrounding glaciers. Yet high-precision monitoring instruments detect subtle movements invisible to the human eye. Sensitive equipment measures tiny displacements occurring over months and years, revealing that certain sections of the mountain are continuously adjusting to changing internal conditions. These measurements provide one of the clearest demonstrations that even Earth's most iconic peaks remain active geological systems rather than static monuments. Matterhorn's instability does not imply imminent collapse of the entire mountain. Such sensational claims have no scientific basis. Instead, the danger lies in the increasing frequency and unpredictability of localized rockfalls. Individual pillars, detached blocks, and fractured cliff sections may fail with little warning as warming continues to alter the balance between rock strength, ice, and gravity. Researchers emphasize that these are natural processes being accelerated in many high alpine environments where permafrost has historically provided additional structural support. That scientific understanding has become increasingly relevant during the current climbing seasons. During 2026, periods of unusually warm conditions have contributed to elevated rockfall concerns on the Matterhorn. Local mountain guides have at times advised postponing summit attempts because thawing permafrost and unstable rock have increased objective hazards along portions of the classic Hernley Ridge. Even as experienced guides note that climber-triggered rockfall can also contribute to the danger on this heavily traveled route. Far above the valleys, the changes unfolding across the Matterhorn are measured not in dramatic daily transformations, but in painstaking scientific observations collected over many years. Laser scanners sweep its cliffs with millimeter precision. Temperature sensors buried inside the rock record the slow migration of heat. Satellite measurements detect tiny surface movements. Drones repeatedly photograph unstable faces from angles impossible to reach on foot. Together, these instruments reveal that the famous peak is constantly adjusting to the loss of the frozen bonds that helped stabilize it for thousands of years. One of the greatest misconceptions surrounding alpine rockfalls is the belief that mountains simply break when they become too old. Geologists describe a far more complex sequence. Every collapse begins with the gradual accumulation of stress inside fractured rock. Existing joints widen almost imperceptibly. Water penetrates deeper into the mountain. Repeated freezing and thawing enlarges microscopic cracks into fractures visible from several yards away. Gravity continuously pulls detached blocks downslope, while warming temperatures remove the ice that once acted as a natural reinforcing material. Eventually, the resisting forces become smaller than the driving forces, and failure occurs. Matterhorn contains thousands upon thousands of discontinuities that divide the mountain into individual rock blocks of vastly different sizes. Some are no larger than a suitcase. Others measure tens of feet across. Entire cliff sections consist of stacked blocks separated by fractures created during the alpine mountain building event tens of millions of years ago. Those fractures were never completely healed. Instead, they remained hidden weaknesses waiting for erosion and changing environmental conditions to exploit them. Scientists now recognize that permafrost occupies many of these fractures. Rather than existing as one continuous frozen layer, alpine permafrost forms a complicated three-dimensional network of ice-filled joints extending deep into the mountain. Depending on elevation, slope orientation, and sunlight exposure, frozen rock may extend several hundred feet beneath the surface, although the thickness varies considerably from one location to another. As atmospheric temperatures have risen, this frozen network has begun retreating upward. Measurements collected throughout the Alps show that ground temperatures within high-elevation permafrost have increased significantly over recent decades. Some monitoring boreholes indicate warming approaching several degrees Celsius compared with conditions recorded during the late 20th century. Although such changes sound small, they are enormous for rock that historically remained permanently frozen just below the melting point. Researchers studying the Matterhorn discovered that the warming process is not limited to heat entering from the surface. Meltwater generated during warmer periods seeps into open fractures, carrying thermal energy directly into the mountain's interior. This allows thawing to occur much faster than would be expected through simple heat conduction alone. The consequences become visible only after the internal structure has already weakened. One of the best documented examples occurred along the Hernley Ridge during the summer of 2023. Scientists had already installed monitoring instruments around a detached rock pillar that appeared increasingly unstable. Their equipment detected progressive movement before the collapse eventually occurred. The detached block measured roughly 20 cubic meters in volume, equivalent to approximately 706 cubic feet. Depending upon the density of the surrounding gneiss and metamorphic rocks, the fallen mass likely weighed between approximately 50 and 60 metric tons, or roughly 55 to 66 short tons. While tiny compared with the mountain itself, a block of that size contains enough rock to completely destroy climbing routes below and would have been unsurvivable for anyone caught in its path. Detailed reconstruction showed that the collapse did not result from a single warm afternoon or isolated weather event. Instead, it followed years of progressive weakening. Water repeatedly entered fractures, transported heat into frozen joints, reduced friction, and gradually increased displacement until the remaining resistance could no longer support the block. The mountain had effectively been preparing for that collapse over many seasons before gravity completed the process. This finding changed the scientific understanding of alpine rock stability because it demonstrated that water acts as more than a passive participant. It actively accelerates internal degradation by delivering heat precisely where frozen fractures once provided structural reinforcement. The amount of rock naturally shed by the Matterhorn each year varies enormously because rockfalls occur irregularly. Most involve relatively small fragments measuring only a few cubic inches or several cubic feet. Others release several cubic yards of material. Occasionally, much larger failures detach hundreds or even thousands of cubic meters of rock in a single event. Across the European Alps as a whole, inventories maintained by researchers show that warming permafrost has contributed to a noticeable increase in high-elevation rockfalls during recent decades, particularly above elevations where permanently frozen ground historically existed. Matterhorn has become one of the most carefully monitored examples because its steep geometry and immense popularity make every instability event especially significant. Some individual rockfall events documented on the mountain have released several hundred cubic meters of material, equivalent to more than 10,000 cubic feet of fractured rock. A collapse measuring 500 cubic meters would contain approximately 17,657 cubic feet of debris and could weigh well over 1,300 metric tons, or approximately 1,430 short tons, depending upon rock composition. Failures approaching 1,000 cubic meters would exceed 35,000 cubic feet and involve masses comparable to several fully loaded commercial airliners. Fortunately, collapses of that magnitude remain relatively uncommon. Far more frequent are repeated small failures that gradually reshape ridges, gullies, and cliff faces. These constant adjustments slowly remove unstable material while simultaneously exposing fresh fractures to weathering. Laser scanning surveys demonstrate that cliff faces change more often than casual observation suggests. By comparing repeated three-dimensional scans collected months or years apart, scientists identify newly detached blocks, widening fractures, and subtle surface deformation. Many of these changes would remain completely invisible without modern technology, because they involve movements measured in mere millimeters or centimeters before eventually accelerating. Satellite radar techniques provide another remarkable window into the mountain's behavior. Using repeated passes from orbit, researchers measure ground displacement with extraordinary precision across inaccessible slopes. Even tiny shifts accumulated over months become detectable, allowing scientists to identify sections gradually creeping toward failure. The mountain's famous ridges experience different rates of deterioration depending upon their orientation toward the sun. South-facing slopes receive greater solar heating during summer, often accelerating thaw within near-surface permafrost. North-facing walls remain colder but can preserve ice-filled fractures much closer to the surface. Consequently, stability varies considerably across different parts of the mountain rather than changing uniformly. Elevation also plays a critical role. Near the summit, freezing temperatures still dominate much of the year. Lower sections spend longer periods above freezing, increasing opportunities for water infiltration. Between these zones lies a particularly sensitive transition where temperatures frequently oscillate around the freezing point. Scientists consider this belt especially vulnerable because repeated freeze-thaw cycling generates powerful mechanical stresses while simultaneously degrading the remaining permafrost. Gravity amplifies every weakness. The Matterhorn rises almost 5,000 feet, or roughly 1,500 meters, above the surrounding valleys with exceptionally steep faces. Some cliff sections approach near vertical inclinations exceeding 70 degrees. On slopes, this steep, detached material requires very little encouragement before beginning its descent. Once movement starts, rockfalls rarely remain simple. Falling blocks frequently strike projecting ledges, shattering into hundreds or even thousands of smaller fragments. Each impact transfers enormous energy into surrounding rock, occasionally triggering secondary failures. The resulting cascade rapidly transforms a single detached block into a fast-moving torrent of debris racing downslope at highway speeds before spreading across snowfields, glaciers, or talus deposits below. For climbers, this evolving geological reality has become increasingly important. During recent climbing seasons, guides have repeatedly adjusted departure times to reduce exposure beneath unstable sections before daytime warming increases rockfall activity. Early morning ascents, once chosen primarily for firmer snow conditions, now also provide an additional safety margin before solar heating reaches its daily maximum. During the 2026 climbing season, Swiss authorities and mountain professionals have continued issuing periodic warnings whenever prolonged heat episodes elevate rockfall hazards. These advisories are not based on speculation, but on decades of accumulated monitoring showing a clear relationship between unusually warm conditions, permafrost degradation, and increased instability across high alpine terrain. Researchers emphasize that Matterhorn is not unique. Similar processes are affecting Mont Blanc, the Eiger, the Grand Jorasses, and numerous other high peaks throughout the Alps. Yet Matterhorn remains one of the world's most recognizable natural laboratories, where every fracture, every newly detached block, and every carefully measured millimeter of movement contributes to a deeper understanding of how mountain landscapes are responding to a warming climate. Far from being an immovable monument carved permanently into the skyline, the Matterhorn continues to evolve exactly as mountains have throughout Earth's history. The difference today is that scientists can now watch that evolution unfold almost in real time, measuring individual rock blocks weighing dozens of tons as they slowly loosen their grip on one of the most iconic summits ever created by continental collision.